So immensely powerful. It's enough for this slide. And when that happens, the temperature of this neutron star, that's enough, we don't need that anymore. The temperature of this neutron star would become exceedingly high, hundreds of millions of degrees, and at this very, very high temperature, the object would emit practically only X-rays. The higher the temperature, the shorter the wavelengths, the higher the frequency of the electromagnetic radiation, it would emit, no second slide, just turn this one off, that's enough. You can just turn it off. Yeah, thank you. So, the very first binary system, X-ray binary, that was discovered in 1971 was independently discovered by two groups. One group, Paul Murdin and Louise Webster, and the other group was Tom Bolton. And they were studying an X-ray source, a very bright X-ray source, which had the name Cygnus X1. And they measured the star, the optical star, very closely. And they noticed something peculiar when they looked at that star. All stars, including our sun, when you look at the spectrum, have beautiful colors, but there are certain areas in the spectrum where it is dark. We give them a name, we call them absorption lines. Our solar system, our sun itself, has hundreds of these dark lines. And these dark lines tell you something about the molecules and the atoms in the atmosphere of the star. So almost every star that you look at, you see dark lines, absorption lines. And now there is a very bizarre phenomenon, and we call that Doppler shift. And that is, if I have a light source and I move the light source to you with a high speed, it becomes a little bluer, and if I move it away from you, it becomes a little redder. One is called blue shift, the other is called red shift. Most of you are familiar with Doppler shift, not with light, but you are familiar with Doppler shift of sound. You've had that in high school. And I want you to hear that. But sound, I can make you hear. I have here a tuning fork, 4,000 hertz. 4,000 hertz. If I move that tuning fork in your direction, then there is a Doppler shift, and the Doppler shift makes the pitch go up. And if I move it back fast, then you hear a pitch which is a little lower than 4,000 hertz. That's what Doppler shift is all about. The fastest that I can move my arm, I've tested that many times, is about 1 meter per second. 1 meter per second back, 1 meter per second. And you can calculate, since the speed of sound is 340 meters per second, that the 4,000 hertz, if I do this, you would hear 4,012. If I do this, you would hear 4,000 minus 12. And so I'm going to first work on you guys. You just relax, and then I will do it on you. So I'm going to make it 4,000, and then quickly move this back and forth. And what I want you to hear is the difference, the high pitch, low pitch, high pitch, low pitch, high pitch. And the difference is then roughly 24 hertz. Who did hear it? Who did not hear it? Be honest, just say no. You didn't hear it? Okay. You get what you paid for, right? It wasn't very much. You hear it now? Good. Here. You hear the pitch things? Okay, now, stars don't do this. What stars do, in a binary system, they go around. So what I have here is a whistle, and at the end of a whistle is a string. So now I'm going to rotate this string around, and when that whistle comes to you, you will hear the pitch a little high, and when it comes to you, you will hear the pitch a little high, but when it goes away from you, you will hear the pitch a little low. So as I rotate it around, you now hear the pitch go up, pitch go down, pitch go up, pitch go down. And for the mathematicians in my audience, you will hear, if you plotted the frequency as a function of time, you will get a sinusoid. So let me do this first. Can you hear the pitch go up and down? So it goes up when it comes to you, and it goes down when it goes away from you. But now is the amazing thing. If you plotted this period, and if you plotted exactly the frequency as a function of time, then you can calculate the speed with which it moved to you, because you know how much the pitch went up, because you know how much it went down, you know how much it went up. So even if you closed your eyes, you could tell me, if I gave you enough time, what the speed was with which I rotated it. That's number one that you learn. But you learn more. Because you also hear that it repeats itself. And so the repetition is exactly the period, the orbital period. So you know the period that it goes around. You can close your eyes. You can tell me later, Walter, you moved it every 1 second around. You can tell me what speed it was. And if you know the speed and you know the frequency, believe it or not, you can even calculate the radius of the string. And I'll leave you with that knowledge because that is enormously difficult. V equals omega r, for those of you who remember that. And if you know omega and you know V, you can calculate r. So let's now turn to the star. So here is this donor star, which shows a black line. We pick one line. And the donor star is doing this, going around. They're going around. The black hole or the neutron star is going around the donor star. And these optical astronomers, they looked at this absorption line. This is the black absorption line, and they saw this. And they knew when it was moving towards the blue that the star was coming to them. And they knew when it was going to the red in the spectrum that the star was going away from them. So they knew the period, 5.6 days. They said Cygnus X1 is a binary system with an orbital period of 5.6 days. They also knew by how much the movement was, by how much the pitch change was, so to speak. It didn't do this, no, it did only this. So they could calculate the speed of the star, just like you could calculate the speed of the star from the pitch change. So now they know the speed of the donor, they know the orbital period of the system, so they know the radius, because V equals omega r. We all agreed on that just a few minutes ago. So they know out of the simple measurement that they see the black line go back and forth, they know the radius of the orbital system, they know the velocity of the donor star, and they know the orbital period. They were able, with that calculation, to convincingly show that the compact object, the accretor, was more massive than 3 times the mass of a neutron star. And therefore they concluded it had to be a black hole. In the beginning there was an enormous amount of opposition in the community. They didn't believe it. It's now generally accepted. Cygnus X1 is a black hole. It is a donor star. You I will show you the donor star. It is in orbit with a black hole. They have an orbital period of 5.6 days. The black hole has a mass of 15 times the mass of the sun. And the donor star itself has about 30 times the mass of the sun.